Module 8, Nutrients involved in antioxidant function. Atomic structure and free radicals. Atoms are the fundamental units of matter, comprising everything around us. Understanding their structure is crucial in comprehending the behavior of matter at its most fundamental level. So, let's dive deep into the structure of an atom and uncover its intricate components. Discovering subatomic particles revolutionized our understanding of atomic structure. There are three primary particles that make up atoms. The three primary subatomic particles are electrons, which are negatively charged particles orbiting around the nucleus. Protons are positively charged particles located in the nucleus. Neutrons are electrically neutral particles also found in the nucleus. The nucleus is the central region of the atom, composed of protons and neutrons. Protons carry a positive charge and contribute to the atom's overall positive charge. Neutrons have no charge and provide stability to the nucleus. Electrons are negatively charged and occupy specific energy levels, electron shells, around the nucleus. Each energy level can hold a limited number of electrons. For example, the first energy level holds a maximum of 2 electrons while the second energy level holds a maximum of 8 electrons. The image below shows an atom with its first energy level filled. When two or more atoms combine, the newly formed structure is now called a molecule. In order for atoms to combine with one another, electrons may be either gained or lost. During metabolic reactions, electrons can be transferred from the atoms of one molecule to the atoms of another molecule. Each of these situations has a specific name. When atoms are lost, it is called oxidation. When atoms are gained, it is called reduction. For example, hydrochloric acid and sodium hydroxide react. The chlorine from the hydrochloric acid reacts with the sodium from the sodium hydroxide. The sodium atom loses an electron, making this an oxidation reaction. At the same time, the chlorine gains an electron, making this a reduction reaction. Now that we have covered the structure of an atom in general, let's discuss free radicals. Free radicals are highly reactive molecules that possess an unpaired electron in their outer energy level. They form through normal metabolic processes or external factors such as pollution, radiation, alcohol consumption, poor diet, and smoking. Examples include superoxide anion, hydroxyl radical, and reactive oxygen species. This uneven pairing of electrons can cause damage to molecules in the cell by the free radical. Health and free radicals. While free radicals can often lead to cell damage, it is worth noting that they are often formed as a byproduct of healthy metabolism. Many diseases are linked to free radical damage including cancer, heart disease, diabetes, arthritis, cataracts, kidney disease, Alzheimer's disease, and Parkinson's disease to name a few. A natural way to combat the effects of free radicals are with antioxidants. Antioxidants are chemicals that interact with and neutralize free radicals, thus preventing them from causing damage. Antioxidants are also known as free radical scavengers. The body makes some antioxidants naturally, while other sources include fruits and vegetables. Here are some common antioxidants. Vitamin E is a fat-soluble vitamin made from tocopherol. Its functions include protecting polyunsaturated fatty acids, PUFAs, and low-density lipoproteins, LDLs. However, its main function is as antioxidant. Sources include vegetable oils, nuts, seeds, wheat germ, and soybeans. Consuming too much vitamin E can cause nausea and diarrhea. Consuming too little may result in fragile red blood cells, erythrocyte hemolysis. Vitamin E deficiencies are uncommon, though. Vitamin C is a water-soluble vitamin that must be consumed in the human diet. Major functions include the synthesis of collagen, preventing the disease scurvy, enhancing the immune system, enhancing the absorption of iron, and the regeneration of vitamin E. Sources of vitamin C include fresh fruits, especially citrus fruits such as oranges, lemons, pineapples, and vegetables. Cooking foods high in vitamin C will lower their effectiveness, as high heat destroys the vitamin. Consuming too much vitamin C can cause nausea, diarrhea, nosebleeds, abdominal cramps, iron toxicity, and kidney stone formation. The most common vitamin C deficiency disease is scurvy, which can develop after only 1 month of a vitamin C deficient diet. A carotenoid is a fat-soluble plant pigment that the body stores in the liver and adipose tissue. Functions of carotenoids in general include enhancing the immune system and protecting the eyes and skin from ultraviolet light damage. Some carotenoids, such as beta-carotene, can be converted by the body into vitamin A. Beta-carotene is a provitamin, inactive precursors that must be converted to the active form of a vitamin in the body. Beta-carotene is most effective against oxidation in cell membranes. Sources of beta-carotene include fruits and vegetables that are red, orange, yellow, and deep green in color. Consuming too much beta-carotene does not appear to be toxic. It may, however, turn your skin a shade of yellow/orange at high intakes. This is ultimately harmless and reversible. In contrast with vitamin C, cooking foods high in beta-carotene enhances their absorption. Additionally, there are no known beta-carotene deficiency symptoms. Free radicals can cause DNA mutations by damaging its structure. Mutations in critical genes, such as tumor suppressor genes and oncogenes, can lead to uncontrolled cell growth and the formation of cancerous tumors. Cancer develops in 3 basic steps. Step 1 is initiation, where the cell's DNA is mutated. Step 2 is promotion, when an altered cell repeatedly divides. Step 3 is progression, where cells grow out of control. Factors that increase cancer risk include exposure to carcinogens, substance capable of causing cellular mutations that lead to cancer, such as tobacco, obesity, alcohol consumption, a sedentary, inactive lifestyle, infectious agents such as STDs, sun exposure, ultraviolet radiation, environmental/occupational exposure. Another condition where free radicals play a role is anorexia nervosa. Anorexia nervosa is an eating disorder characterized by self-imposed starvation and a distorted body image. It primarily affects young individuals, with a higher prevalence in females. The condition eventually leads to significant energy and nutrient deficiencies. Key to the connection between anorexia nervosa and free radicals is oxidative stress. Oxidative stress is an imbalance between the production of free radicals and the body's antioxidant defenses. Free radicals are highly reactive molecules that can damage cellular components. Studies have shown increased markers of oxidative stress and decreased antioxidant enzyme activity in individuals with anorexia nervosa. Symptoms of anorexia nervosa include extremely restrictive eating practices, self-starvation, intense fear of weight gain, amenorrhea, which means no menstrual periods for at least 3 months, unhealthful body image, and denial of the seriousness of low current body weight.